Así que hablo de feedback como cuando entonces. Sobre movies. Will be taking the serious like
నెట్ వచ్చి
better than the like maybe it's like University more particular life challenges. Karena nanti ada saya udah belum sih? No, no issue sir. You can join the after also. Yeah.
Sagar, password.
Kita 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 Yes. Kita tahu kami itu apa. Yes.
Hotspot. Tell me, I'm still getting Airtel. Rain 3 years. तर यूट्यूबरे किए क्वेश्चन पचारुछन् सुचित्रा महांती देवी प्रसाद पाणी आर्ट्स सेक्शन नहीं सेकंड नहीं देवी प्रसाद क्वेश्चन पचारुछन् फीडबैक get the message that's ready to open. These little messages. Speed ଅଛି। Give full stop। YouTube on। कौन कौन कटी लगी। Sorry, हाँ बोल। हाँ हाँ देखो हाँ
Actually, more about it. Actually, got a webinar channel, and it has a 3 to 4:30 ଅଛି। ମୁଁ ଯଦି free ହେବି କୋର୍ସ ତାହେଲେ ଆପଣ ଆମ ଅଫିସରେ ମାଷ୍ଟର ଆପଣ ତାଙ୍କ ଯୋଗାଯୋଗ କରନ୍ତୁ ଇନକେସ୍ ନ ହେଇପାରୁଛି କାହିଁକି ଆପଣଙ୍କୁ ସବୁ ପ୍ରୋସେସିଂ ଦେଇକି ତାଙ୍କ ଫାଇନାନ୍ସକୁ ଅବଜେକ୍ସନ କଣ ଅସୁବିଧା ଦେଖନ୍ତୁ ଆମେ ଯଦି ପଛରେ ମାନେ କଣ କିଏ ମାନେ ହବ ସେମାନେ କହିବେ ଯେ ଆପଣ ତ ଦେଲେନି ଆପଣ ପୁଣି କଣ ସୁବ୍ରତ ପଟ୍ଟନାୟକ ଡିଲ୍ କରୁଛି। ହଁ ନା ସେ ମେଲରେ ପଠେଇ ପାଟିରେ ଚଳିବ ନା 7873 74 737 7873 737। Surprise after उनका जो मनोज कुमार दास ने ये मोड़ा काहे नहीं पूछ लिया कौन कर दे सिखाए मोड़ा पैसे और जरा ना जानो अस्सी डॉलर के मतलब नॉट इंटरेस्टेड बोले सर वो मोड़ा तो देख लीजिए देख लो
Sir, good afternoon, sir.
Presenting.
Hello, sir. Good afternoon. আপনার মাইকটা অনমিউট করুন।
Afternoon. Can you see me now?
Yes, sir. I can see you.
All right.
Sir, namaskar.
Namaskar. How are you, sir?
Sir, fine, sir.
Sir, he is the head of the department of our department.
I know.
Okay, namaskar, sir.
Okay, so you'll should I share the screen or I'll do it later?
Just a couple of minutes.
Okay. Yes, sir. A couple of minutes.
ଆପଣ କହିଲା ବେଳେ ଖାଲି ଅନ୍ କରନ୍ତୁ।
Now we right bomb.
So how was the morning session? Went well?
Yes, sir. Sir, it was
Sir,
fine.
Professor Misra presented a good talk. Okay. Good. Glad to hear that. Yes, sir.
Sir, actually, we're happy
To get you
for our
webinars. No.
Sir,
It is.
at the same time, I request you to come to our place.
You
You should just
decide a date so that
it will
you
become
have to invite me.
Yes, sir.
Yes, sir. This is
Sir,
This is the initial point.
Sir,
Next, we must welcome you
for
to our department. Definitely. Yeah, well, I mean, the problem is with the COVID time now, things are completely. Yes, that is the problem.
Yes,
Yes,
sir.
sir.
But
But the situation is okay, then you must be invited and you will give some time to
visit our
our
place.
place. Sure, definitely, we'd love to. Yes, sir. Will you start?
Sir, will you start?
Yeah, I'm fine. Okay.
Anyway,
Good afternoon to all.
Namaskar.
Namaskar.
At
At the
second
second
session,
session,
I
I
welcome
welcome you all once again.
Now
Now
I
I
request
request
Dr.
Dr.
S.N.
S.
Sahu,
Sahu,
convener
of this webinar,
to
to
give
give a brief introduction
of
of
Professor
Professor
Sundar
Sundar
Gopal
Gopal
Ghosh.
Ghosh.
I
I
also
also
welcome
welcome
behalf
on behalf
of our
of our
department,
department,
the Department of Chemistry, Paramapur University.
Department of Chemistry,
Yes,
Paramapur
sir.
University. Yes, sir. Satya, sir.
Good afternoon, everyone. It gives me immense pleasure to formally introduce Professor Sundar Gopal Ghosh,
the
the speaker of the second session of the national webinar organized by Department of Chemistry, Paramapur University.
This is
This is a short biodata of Professor Ghosh. Professor Ghosh did his masters in chemistry from Science College, Calcutta. He obtained his PhD degree in inorganic chemistry from IIT Bombay in the year 1998 under the guidance of Professor Pradeep Mathur. His topic of research was isocarbyl complexes of group 6 transition metals and chalcogen stabilized diiron clusters. Then he moved to University of Notre Dame, USA for his postdoctoral research with Professor Thomas Fellner, where he developed a new synthetic route to hypoelectronic metalloborine clusters. He joined the Department of Chemistry at IIT Madras as an assistant professor in the year 2005. Currently, he is working as a professor in the Department of Chemistry. His research interest includes metalloboranes of polytransition metals and rare earth metals and their application in catalysis, transition metal diborane and diborane complexes and their applications in catalysis. He was recipient of several awards, starting from the prestigious AGH Fellowship, Alexander von Humboldt Fellowship, in the year 2007, CRSA Bronze Medal in 2012, Professor Piranjan Roy Memorial Award in 2018. He is a Fellow of National Academy of Sciences, Fellow of Indian Academy of Sciences. He is the member editorial advisory board of organometallics during 2018 to 20. Currently, he is a member advisory board Journal of Indian Chemical Society and member editorial board Inorganic Chemica Acta. So far, Professor Ghosh has guided 4 postdoctoral students, 23 PhD students, and 22 MSc students. He has published more than 200 research papers with very high impact factor. I am very happy to announce that I am the first PhD student of Professor Ghosh, and one of my lab mates, Dr. Subhankar Kumar Bose, and he will also be delivering his talk tomorrow. So this is a short introduction of Professor Ghosh, my supervisor. Today he will be speaking on diborane to polyhedral borane clusters. So with this short introduction, I request sir to kindly move ahead with his presentation. Sir, the dice is yours.
All right, thank you so much, Sahu. But it was not a short introduction, Sahu. You took
Sir, the opportunity I got to convey my gratitude.
Sure. Thank you. It was nice of you. Just let me share the screen.
Yes, sir.
Can you see it?
Yes, sir, it's coming.
It's nice.
Yeah, it is fine.
All right. Thank you so much. All right. So good afternoon,
Sir, should we go ahead with the full screen?
I did full screen.
But still,
I think there's some problem with the Mac, but is it okay? Is it coming very small or?
no, it's okay. It's okay.
So is it coming two screen or one screen?
I mean, one screen, but I mean, you need to do like the full screen. I mean, has not come yet.
I did full screen though. Is it okay? So is it fine?
Yeah, it's okay. You can go ahead. Yeah, fine, sir.
Can you hear me?
Yes, sir. Yes, sir. Perfectly.
Sir, absolutely audible. Yeah, I can. We can hear you.
So just see, please let me know if you find it's better now. Sahu, is it better or the same?
Yeah, maybe it's. I mean, delay in because of network.
Okay, I don't know why it is happening. So should I go ahead with the presentation because
Yeah. Please go ahead, sir.
So is it clear?
Yeah,
It's clear. It's visible, sir.
Okay, good. Okay, so good afternoon and welcome to my talk. Before I begin, I would like to give my sincere thanks to the organizers, particularly Satyanarayana Sahu, for inviting me to give this the lecture in this forum. It was nice of you. I hope that that the others, whatever things over and going to be tomorrow, successful and the students get benefited with all the different types of science that will be delivered. Okay, as you could see that the topic today is a diboron to polyhedral boron clusters. From the title, it's very clear that I am going to talk about a boron chemistry. As you all know that boron being next to the carbon in the periodic table, it has a lot of similarities in terms of your the structures, geometries, but boron being electron, just 1 second please. Stop sharing. This? Yeah. No? Should I do the slideshow? Send. Please excuse me because I have some issue with the. Is it coming? It's like this. So if I go next one, this time. Stop. Got it. What happened? Here. Where is it? Okay. Why not? Okay. Sahu, can you hear me?
Yeah, sir, we
Yeah,
can
sir,
hear
yes,
you.
yes,
But
but I mean, two screens are there.
Yeah. So that's okay. I cannot help it now. I think probably I have to.
yeah,
We can go ahead.
we
We can go ahead, sir.
Okay. So as you could see from the title, I'm going to talk about that the boron mostly. So as a boron is next to a carbon in the periodic table, is a lot of similarities. However, as boron is electron deficient molecule, it shows a lot of structural varieties, bonding, different geometry, structure, and that way we are fortunate so that we could have a different kind of structures, different kind of molecules, and also it shows a lot of different properties unlike carbon. With that, the boron molecules have been utilized with a lot of boron chemists, and as you see here in this screen, I have listed some of the applications, particularly the first one is you have boron nitrogen, in which they can get a hydrogens from the amine borane or ammonia borane that could be utilized as a hydrogen storage material. Then the right hand side, you have a carboron molecules that could be utilized for the boron neutron capture therapy. Hydroboration, H.C. Brown discovery, you all know this is so common in organic chemistry. Then you have borons in medicine, boron nitride, carbide, very good materials for many of the solid state applications. So as metal borides, borosilicate glasses, you all know. There are a couple of more examples I had listed here on the left hand side. As you could see that this is a carborane superacid with all the hydrogen substituted by a chlorine. And then another one is a is a thermal stability polymer that is also based on the carborane materials. So there are a lot of applications on the boron chemistry. I have just listed few of them. This is the one I was talking about, that the amine boron complexes. If you have a catalyst, you can generate hydrogen, and that could be utilized for the energy. And then many people are working on the synthesis of different metal hydride, borohydride complexes, and try to figure it out whether they could be utilized as a hydrogen storage material. Then this is these are all there in the textbook. You see all those different types of boron nitride. This is the hexagonal, the first one, which is very, very soft, electrical insulator, and then it has a very high thermal conductor. It's a lubricious, inert, non-wetting, and the other variant, which is the cubic boron nitride, which is equivalent to that of a graphite, equivalent to that of a diamond, and it has a tetrahedral structure, and it has a lot of similarities with the carbon. This is the one I was talking about, like boron nitride. It has a layer structure as the graphite one, and this is very, very lubricant. And this material been used in many of the cosmetic industries. GE is one of them that they use it for their this cosmetic industries. This is one I was talking about, a carborane-based material they used for the boron neutron capture therapy. So what is boron neutron capture therapy? You take a carborane with a thermal neutron with enriched 10 boron, and if you bombard this one with, if you have it enriched 10 boron, if you bombard with thermal neutron, it emits a lot of energy in terms of 7 lithium and 4 helium. That can kill the tumor cell. And good thing about this therapy is that here this energy does not travel too much to your cell, so it can very nicely kill the target cell. Then you have a borofin. You all heard about the graphene material, one of the very good discovery, and got the Nobel Prize also. So similar to that graphene, borofin materials can also be synthesized, and this material, sorry, this material, can you see it, Sao?
Yes, sir.
Yes, sir, it is visible.
Thank you. Now, as compared to a graphene material, borofin can also be synthesized, same as that of the graphene with a single layer. But as boron has one electron less, so it always end up getting a hexagonal hole. And this is good in terms of the material. You can tune the property of this borofin. The only problem with the borofin is that this material has not been synthesized. As you could see that this is a very recent discovery, 2015, 2014, made by one of my very good friend, L.S. Wang in Brown University. But this material, if it is synthesized in bulk, and fantastically, it could be utilized very fantastically in terms of your different properties, as you see with the graphene material. Then MgB2, it was known for a long time. However, it was very recently turned out that to be exciting superconductor at 40K. So that means many of the materials, although it was known earlier, people have not explored their properties, and this is one of the very good examples. So I can go on and on with the different types of applications of the boron compounds, boron materials, and due to that, a lot of people biggest contribution to this field and got recognition. Few of them, you know, that Lipscomb, who got the Nobel Prize, and H.C. Brown for the hydroboration. Then there are a few more, Negishi, Suzuki, they have got the Nobel Prize, that also boron chemist. And many people, the contribution Waite's rule everywhere, I'm sure that in your university also is been taught, the Waite's rule, Mingo's rule. So this is a very, typical of some of the people who contributed enormously. I have not listed some of them like Frederick Hawthorne, Fellner, many others. But these are the people who their contribution at the early stage of the chemistry, particularly Alfred Stock, who started in 1912 on the Schlenk-Klein technique, beginning of a boron chemistry, so on and so forth. All right, so now I move into the chemistry that I plan to talk today. What typically we do is we take different types of a metal polychloride materials, it could be metal carbonyl materials, it could be metal hydrides that I have listed down, and then you treat them with sodium borohydride or lithium borohydride. So what happened, as you have a metal, as you have a chloride, you are treating with a metal borohydride, it's a reducing agent. It leads to the formation of a metal polyborohydride, which is very unstable. So now it has a two pathway. One way it can release hydrogen, another way it can release boron, and based on that you get two different types of material. One leads to the formation of different hydrides, another one leads to the formation of your metal of boron. So that's the interest we had. So that depending upon the metal, you get this material stable, unstable, and we have explored this chemistry, a majority of the chemistry in the beginning of my career. I started, Sahu also did a lot of chemistry with this CP metal chloride and lithium borohydride. So the interesting part in this slide is that if you see on your left-hand side and if you see on your right-hand side, left-hand side I had listed all the materials that deal with the late transition metal, and the right-hand side you have all those metal clusters and a simple boron complexes in which you have a lot of hydrogens. So that is mainly because a early transition metal has a less electron in the d orbitals, and that's why you need electrons that is fulfilled in terms of your hydrogen. So I'm going to talk today some of the chemistry both in terms of the cluster and some of the chemistry that was very interesting, which was a diboron. So the first part I'll focus on cluster chemistry. There I'll talk about some of the case studies. I'm not going all in details. I'll talk about some of the case studies. So the first one is your supra-icosahedral. You all know that icosahedral geometry B12 or carborane. It's very well known. This is a geometry which is rotating. You see it's a 12 vertices, highly symmetrical. All the vertices are 5 connected. Now people try to make a similar kind of molecule, not with carborane, but with a different metal and main group elements. So we also tried to do this chemistry because there are a lot of literature that suggested that geometry beyond icosahedrons are possible. A couple of studies made by Lipscomb and the Scheller, as you could see that in the chart, in the figure. I have put a line, this is called icosahedral sink, in which it has maximum stability. However, 13, 14, 15, 16, as you see here, that is also possible to make. And these are the proposed structure of some of the supra-icosahedral borate anion. I'm going to talk about one of the geometries B16, B16 analogs in a little bit. So this is one molecule that you could see there. This all this green color, they are the metal, and you have a 10 boron. So that means you have a 12 vertices. But what happened? You do not see a icosahedral geometry. Instead, you end up getting some kind of a oblato or flat geometry having a cross-cluster metal-metal bond. So that means this metal-metal bond makes this molecule totally flat, and you do not have a symmetrical geometry. And also, these molecules do not follow any of the electron counting rules that was developed by Waits or Mingos or the Jennings. And that's why it drew a lot of attention in the scientific community. Now, this is one molecule I wanted to share today. One of my students, Deepak Roy, who is now in IIT Indore, so he started this chemistry with the rhodium, and I have just given the structure of the compound because I don't want to go in details of the synthesis. So what happens if you treat this with the lithium borohydride followed by boron pyrolysis? You get this geometry. I'll describe how you can describe the geometry. Suppose if you take a simple tetrahedron, and if you cut all the 4 tetrahedron vertices or the corner, you will end up getting a 4 hexagonal faces. Now, if you cap all these 4 hexagonal faces by a rhodium, as you see, rhodium 3, rhodium 1, rhodium 2, and rhodium 1, you can simply cap it. So you had a truncated tetrahedron cutting the 4 vertices of a tetrahedron, and you can cap it, you get a 16 vertex. So this is the first time we made a molecule having a single case cluster having maximum number of vertices. The same geometry was proposed by Lipscomb, although it was a bit different. On your left hand side, they call it a square, diamond, square. You could see these are all square. So, but similar, like the geometry, a little bit of different. This geometry you can transform it using different kind of diamond, square, diamond mechanism. So when we wanted to do a chemistry similar with the cobalt, so in the case of cobalt, what happened, you do not get a single case cluster, but you get a fused cluster. This is a very complicated geometry. You would not understand this geometry. I'll explain it. So this geometry is a fusion of three different geometries. On your left-hand side, what you see here is a icosahedral. On your right-hand side is a bicap square antiprism, and you have a tetrahedron. Now, if you fuse these three geometries, you will get this a fused geometry of this cobalt. Now, whenever we have a fusion, there are two different kind of electron counting rules that can be applied, whether it obeys or not. Fortunately, we have done both of them, Mingo's and Jemys, and very nicely satisfied with the electron counting rule. I have calculated this one and shown it to here, but I don't want to go in details, just to convince that this molecule obey the fusion formalism developed both by Jemys and Mingo's. All right, now very recently, one of my very good friends in Hong Kong who made a similar kind of geometry that was proposed a long back by Lipscomb. That is the one I was talking about, square, diamond, square on the right hand side corner. And this is a first time 16 vertex carbon. What we have developed, that was a metalloboron, and he made for the first time a carbon where B14C2 geometry. So this was a very good discovery. And now these days, nature communication is very open, so they can actually disclose who actually reviewed this paper. Actually, I was one of the reviewers for this manuscript. So it was a very good discovery, and now this could be utilized, this molecule, for a different kind of properties in material science. One of the very interesting properties that currently we are working with Professor Pradeep in the same department, that shows a different kind of luminescence fluorescence properties of these nanomaterials. So this is a big discovery. The yield of this molecule is not that much. So hopefully, I'm sure that they will come up with a good synthetics methodology that they can make it in good quantities, which can be utilized in material sense. Now the next cluster, which is a B7H7 2- borate anion. This is a very interesting one. If you look all this textbook, probably you will not see much studies with this material, particularly with a geometry and the structure. The main reason what claim that this molecule is extremely unstable, whenever this was formed in a solution, immediately it gets converted to the higher borates. So this was very, very difficult. However, in 1967, Mutatis made this molecule first time, and he claimed that this molecule was proven to be very, very difficult to characterize. So it was a very partial characterization. 2011, it was the Bernhard who made the first anion of this B7H7, and that's what we know the geometry. So we have been working with early transition metal, and what happened while working with the zirconium and hafnium with the lithium borohydride and boron pyrolysis, one of the molecule that we have isolated that shows a mass spectrum very close to that of the B7. And indeed, when we got the crystal structure, recorded the single crystal X-ray data, and that indeed shows it's a B7. And this is the first time we have made a B7 in good quantity, in which you have two of these early transition metal CP2 fragment that stabilize this B7 core. So this is the first time neutral B7 molecule, and it was synthesized without any difficulties in good quantity. So this was the good for all of us, because now I think a lot of structure, bonding, all the different kind of properties can be explained that was not possible sometime. We have done some theoretical calculation. I am not going in details. This was done in collaboration with Lysing One, who made this borofene and all those relatex molecule in matrix isolation. And just to convince you that this the bonding of this B7 molecule was very nicely explained, satisfied with that of the that which was not possible earlier because the structures was not known. Now, along with the formation of this B7, we also have isolated another molecule that shows 5 different boron peak. As you see here, the boron NMR, both for the zirconium and the hafnium metal, the mass spectrum shows not B7, but it's a higher cluster. Unfortunately, we had the structure of both the molecule, and that shows a dodecahedral geometry. And it's again now is stabilized in the coordination pair of 2 transition metals, zirconium Cp2 and hafnium Cp2. Now, please note that this molecule, not many molecules are known in the literature in terms of the structures. B8Cl8 was known, and a lot of theoretical calculation I had listed here underneath this B8Cl8. And also you have a B8H82 minus. There are also a lot of studies. So this molecule is very, very precious in terms of their synthesis. And when it comes to their spectroscopic data, that is more interesting, because this is the first time we have shown that this molecule, both in the solution as well as in the solid state, shows a similar kind of geometry, that is a dodecahedron geometry. And also please note that this molecule, as I said, that B7H7, it was synthesized in 2016, and we have been struggling to get a different molecule, and I had listed here underneath Ghosh and Jemi's unpublished result. So in 5 years' time, we could get only one compound. So you know the time, the effort it involves to have a one molecule with this kind of geometry. So this is a lot of work, although it looks very simple, but it is not. It takes a huge amount of time, lot of manpower, lot of different techniques to characterize this molecule. So currently this molecule we are working with, again in collaboration with GEMIS, and hopefully this will be very soon in print. Now, the good thing, as I mentioned to you, that this molecule earlier, when the B8H82 minus was synthesized, what it says that the boron NMR is a kind of is a mystery. In the solid state NMR and the solution state NMR, they do not tally. And first time we had shown that a D2D geometry, that is a dodecahedron, that exists both in the solid state and in the solution state. However, the bicap trigonal prism and the square antiprism, that next two geometries, although they are isomers, it was not isolated in our case. So this is a very clear-cut picture that first time we could show that the dodecahedral geometry, which was theoretically predicted earlier, that the most stable geometry, now we could do it experimentally, stabilizing them in the coordination pair of early transition metal fragments. So with this study, it's now we are going towards a different direction. Whether B13, H13, the first supra-icosahedral borate anion can be stabilized. We have done it B3, we have done B7, we have done B8. Now what about 9, 10, 11 and 12, or a matter of fact B13? So if you could achieve that, that would be really, really nice. But again, please note that to get B7 to B8, it took 5 years. and I have only 15 years of job left. So hopefully we'll get few molecules before I retire. Let's see where we ends up. We'll see. The next molecule that is very, very interesting for many of the boron chemists to have a B6 planar molecule as a benzene. Now you know that benzene is a very flat molecule, and this is one of the proposed structure of C6H6 with vanadium. Now what happened if you try to make a B6H6 flat? In this case, boranes do not form a flat 6-member B6 rings. What happens whenever you have a flat ring, immediately it gets into a cluster. The only possible way you can make it is that if you can make this in an inverse sandwich structure like MB6H6M, in which M is a fragment such as a vanadium CP. That is the one that is shown here in the picture. So we have been working. One of my very good students, Anagha, she has been working in this for last 2 years. And indeed, finally, we could see that a flat B6 is very close to our heart. We got the structure, and now we have done all spectroscopic data except one of the things is missing. That is the connection of the hydrogen. Now, currently, this is under neutron diffraction study in Sydney, and hopefully we'll get the hydrogen connectivities. Now, the beauty of this structure, as you could see here, is that although it's a B6 ring, to support that B6 in a flattened manner, you have 10 hydrogens, 6 terminal and 4 bridging hydrogens in a mu3 mode. Hopefully that we could get this connectivity from the neutron diffraction. And as you could see here on the extreme right hand side, the 6-member B6 ring, it's rotating, and you could see that very nice 6-member B6 ring. So we are very, very excited. We are working with GEMIS again for this, and hopefully this molecule, once it is done, and in no time it should be in the textbook. All right, now I am switching gear from a cluster chemistry to a simple diboron chemistry. Diboron chemistry, you all know, B2H6, it's all taught in undergraduate or in MSc, many schools. I'm sure that in Odisha, I know many of the universities, teachers, they teach, and we get a lot of students from your state where, like students are very, very good answering this boron chemistry. Now, boron and carbon being next to each other in the periodic table, they have a lot of structural similarities, similarities of molecules. Like a boron, you have alkane, boryl, you have alkyl. Boride, you have carbon, it's a carbide. You have a bodylene, you have a Fischer carbene, Schoch carbene. But one that is not available with a carbon is the down I have listed here. Different type of sigma complexes of the boron because of their electron deficient in nature. It's a Lewis acid, it can accept electron from anywhere. And we have isolated many, many molecules in which you have a boride, interstitial boride, where the maximum boride connectivity of a boron is mu9. So you can imagine that boron can extend bond up to 9 numbers. So this is possible because of the boron electron deficient in nature. Okay, so I'm going to spend some time with the diboron chemistry. First thing, especially, is with a borylene. Different types of borylene molecules are known in the literature. You have a free borylene, you have a terminal borylene, triply bridged, base stabilized, T-shaped, semi-bridged. A lot of people are working on this borylene chemistry, particularly when it comes to 2-center 2-electron bonding. But I'm going to talk about some of the chemistry in which a BH unit is stabilized at the coordination sphere of 3 metal. So the thing which came into our mind, this is the molecule made by one of my students, Gita Rani, it's a butterfly. I think Sahu was there that when she was working. Now this molecule, the good thing is that it has two boron, and if you could replace one of the BH vertices by a Fe, so then you will have only one boron left, and that would be a typical a BH a fragment. So with that objective, we have carried out reaction with a different metal carbonyl. And what you see here in this picture, in this scheme, that you have a 3 metal and you have a BH, you have a 3 metal, you have a BH. So with this, we have expanded this this chemistry with all different kind of transition metals. And here we have studied almost all the transition metal, and we have isolated, structurally characterized. Now recently we have written a review. One of the students, actually, she comes from your university, that Alakananda Pradhan. She, along with Saurabh Kaur, wrote this coordination chemistry review, and that talks about all these different borylene molecules. Okay, so then this is a chart that talks about different kinds of diboron molecule. The left hand side, you see diboron 6, then you have a diboron 5, 4, 3, and diboron 2. And the bottom one is a different hapticity of diboron, in which you could see that hapticity 2, 4, and 6. So we wanted to see a chemistry, something was very similar to the Sheldon Shore, who made this molecule. Just excuse me, just need some water. So this molecule was synthesized by Sheldon Shore in 1989. This is a typical diboron. As you could see that it has 5, one of the BHB actually is replaced by FeCO2CP. So you can call this as a diboron 6 analog. So we wanted to see whether a similar kind of molecule with a different transition metal can be synthesized. In fact, we did that with a pentaboron treated with a benzothiazole ligand. And the structure, what you see on the right hand side, is exactly same kind of structure where you have this B2H6 is a kind of analog. Say CO that gives 2 electrons to the Fe center, that is given by the sulfur with a dative bond 2 electron CH. Ruthenium CP and FeCP, they are the same number of electrons. And this B nitrogen bond, which is a simple exopolyhedral kind of bond, you can call, and this gives 1 electron. So this could be a typical analog of the left hand side that is listed. So this one, once we had made, we wanted to just test the reactivities or the molecule with a different transition metal. So in this case, the group 6, we started with another diboron 6 molecule, which is treated with the carbon monoxide. And what we see here, you see this, I'll just directly go into my structure. This is actually diboron 4. You see this in the left hand side extra structure. There are 4 hydrogens with a B2 unit. And this molecule is extremely electron deficient. It took us a lot of time to figure it out what was going on. So one of my students now with me, and already one who is now with doing a Humboldt fellowship, he made this molecule together. They made the molecule together, and it took a really long time to figure it out what was going on because of this NMR. So we are fortunate to have the structure. So once we had the structure of this molecule, we wanted to see what is going on in terms of the electronic structure. So the molecule is similar type with a carbon made by F.A. Cotton in 1978. As you could see in the top one with the molybdenum 2CO4, once it's treated with acetylene, it forms exactly the same type of molecule with acetylene as C2H2 is isolobal with B2H4. So that means this gives 4 electrons to this 2 metal center. And we have done theoretical calculation again with Jemis, and in fact, the student who is now doing postdoc, the Humboldt Fellowship, he was a very good theoretician. He learned this theory all by himself. He did a lot of theory. Although he wanted to get it clarified and verified from Jemis, and we have reported this in 2018. Now, these are the all different types of diboron 4 molecules, in which you see the different type of symmetry. It's a D2A, CS, D2D, C2V, all those different symmetries. And this is the symmetry falls under CS symmetry, and that was typically missing in the literature. So that means now we have all the 4 different types of diboron 4, which are structurally characterized. Now, another interesting part of this molecule is that, so when we treated this molecule with a metal carbonyl, what happened? This molecule, it takes up 2 hydrogen and it forms a B2H2. And you look at the structure of these 2 molecules. Left hand side, you have a diboron 4 where you have a B2H4. And on your right hand side, you have a B2H2. And look at the bond distance of the BB. It's a 1.59. It comes very typical of a BB double bond. So that means we made from alkane to alkene, or you can call it a borane to borine. So this is a diborane in which you have replaced 2 hydrogens from a diborane unit. So you wanted to expand this study with group 5 metals. Unfortunately, this does not form a diborane, but it forms a diborane isoelectronic analog where one of the boron is replaced by the sulfur. So you have a structural. So it was not that interesting. The next one, which is very, very interesting, is your, I'll not go in this one, I'll just go to the next one, is a classical and a non-classical diborane. So the classical, as you see here on the structure number 2, in which you have all terminal hydrogen, and the non-classical, you have a BH, or you can call it a CH hydrogen. So this has been studied with the C2H5 plus, and these are some of the theoretical studies reported. I'm not going in details, I'll directly go into my study. So here some of the molecules known, all reported with a non-classical. So there are no classical diboron 5 was known in the literature. So again, I had a very good student, Kaushik, who started this chemistry with the tantalum. And here we got a molecule, and the structure is here, and the NMR is here. I'm not going all the spectroscopic details, but what I can tell you that in the structure, X-ray structure, you see that there are 5 boron attached, so 5 hydrogen attached to this 2 boron, and 1 hydrogen is attached to the tantalum is tantalum. It is not connected to the boron. So that means it is a B2H5, and you can remove this hydrogen as it goes at H plus. So then you get a B2H5 minus. So this is the first non-classical B2H5. It is reported very recently. And again, it's with collaboration with Jemis. Now, this is a lot of history of this molecule. Initially, we thought something different. And then, this molecule was not satisfied in terms of the theoretical study. So theoretically, what was observed that the most stable form is the one on the left-hand side. And when we had this geometry and we had the structure, initially, as you could see here in the NMR, that there was a peak at 9.24, and we have been ignoring this peak for almost 1 year. we thought probably this could be impurities. And that turned out to be actually metal-age metal. So many times some impurities also should not ignore. You should be, always be careful of the peak what you have. Don't think that something could be impurities. So anyway, this was a very nice studies by Jemis, and this molecule also now recently we have a review in Account of Chemical Research, and they are a part of this the review. If anyone interested, it's registered here. You can just go through them. So this student also now got a Humboldt Fellowship now, so he is moving probably soon to Germany, if of course the COVID allowed to travel. Now, what happened immediately after we reported this? Almost simultaneously, a report by Douglas Stephen. He made a B2H5 cation. So that was very nice, a back-to-back, a anion and the cation. And of course, this was not in a metal center. This was on the coordination sphere of a simple organic molecule. So this was really, really very nice. I get a lot of emails from many colleagues that, okay, it was so nice. Now, B2H5 minus and B2H5 plus both can be introduced in the not an undergraduate, of course, it's in the master studies. Now, this molecule, when treated with the molybdenum, what happens? We wanted to see that whether these two of the hydrogens can be extracted using the molybdenum CO5 fragment. And indeed, when you do that, what happens? Two of the hydrogens is not replaced. What happens? This MoCO3 fragment, it typically coordinates with one of the hydrogens. Now you see the beauty of this, the NMR. The moment it coordinates with the hydrogen, so the chemical shift of that molecule is shifted to very downfield. Earlier it was minus 20, close to minus 16, and now it moved to 20. So almost like 20 ppm shifted on your left hand side. So this was very nice. But this does not remove the hydrogens, but it simply coordinates. So just before the upload of this manuscript, Jemis came up with another very fantastic observation, and that was he did some calculation that shows that the metal, what you see here, this molybdenum is not only coordinated to this one tantalum H molybdenum, but it coordinates with another tantalum also. So we have been asked to record a low temperature NMR. We did, and he was indeed so correct that it shows a two different kind of peak in the at a very, very low temperature. This is the minus 70 degrees centigrade proton NMR that's clearly distinct of the CP star proton. And now here the beauty of minus 6 peak for the NMR got splits up into two peaks. So that clearly shows that at low temperature this molecule gets freezed and you have two different type of metal-age. All right, so this is another molecule of a diborane in which you have a different kind of hapticity. We wanted to do with a different type of ligand, not with a cyclopentadienyl or a different chelate ligands. We wanted to introduce something different where you have a lot of flexibility in terms of that leaving group. So this one was with rhenium and manganese CO10. We treated with a borane, and what we see here, all different types of diborane molecules. I had listed here the structure of one of the diboranes. This is a symmetrical diborane 6, in which it is connected with the 3 metal with hapticity 6. This is one molecule in which one of the metal rhenium bond is dissociated or it's broken, and because of that the spectroscopic data is totally different at a low temperature. In the room temperature, as you could see there, this very broad peak are not distinct, but at the low temperature, you see all the 5 different metal HBs are distinct, and that shows that it has one metal boron bond not exist in this molecule. So this type of molecule again is very well known in the literature. One of the good examples listed in the Greenwood textbook. If you look at the example of MnCO4 B3H8 molecule, if you heat it up, what happens? It loses carbon monoxide one, and from a arachnogeometry, it forms a tetrahedral geometry. And if you if you put carbon monoxide, it goes back to the arachnogeometry. So this was similar thing observed in our case also, in which you have a release of carbon monoxide, it breaks a metal boron bond, and if you put carbon monoxide, it can get back to the. So this was one of the very good examples that satisfied some of the old examples of the manganese. We have done another trick to make a diboron molecule. That was the phosphine-induced cleavage of the metal. We had the same type of molecule with the manganese, with the B2H6, with the 3 manganese. We treated this. So this studies again was done by your student, your university student, by Alakananda, in another senior student. So probably I'll encourage and request to you, all the teachers, to send good students from universities, and it will be really nice. So this was treated with a PCOI3, and what found is that it breaks up one of the, it eats up one of the manganese fragment, and you get a base stabilized diboron, and another diboron in which you have a one metal that is almost is like a manganese boron is 180-degree angle. So this was the very first time we have shown a diboron connected with a metal, and that also due to the presence of a PCOI3, a good sigma donor ligand, it pumps a lot of electron to the metal and makes this manganese boron bond very strong. And as you see here, manganese boron bond is 1.92 angstrom, which is typically is not the case for many metal boron bond. It usually around 2 or more, but due to the presence of this, it shows a very, very strong. We can almost call this as a manganese boron double bond. All right, the last part of my talk, another student of mine, Jafar, he'll be very angry if I don't talk about his chemistry. This is very fantastic chemistry, but it's a lot of chemistry related to the metal ligand, cooperativity, MLC. This is very well known these days. This is not my idea, so I'm not going to talk much about this. But what happens is that in this metal ligand cooperativity, in both the metal and the ligand takes part in different kind of catalytic cycles, small molecule activations. And these are all different types of chelating ligands. It is with the nitrogen oxygen, it is with the nitrogen sulfur. Many examples are known. And we had utilized some of the nitrogen sulfur ligands. So this was the first study made by him. Started with a ruthenium cymene phosphine chloride, treated with a benzothiazole borate ligand. What he observed that a formation of a ruthenium nitrogen carbon sulfur heterocycles, and this molecule found out to be extremely reactive to different small molecule activation, and probably this molecule could be utilized in different type of catalytic activities. Some of the catalytic activities with this kind of molecules I have listed here, such as BH bond activation, SiH bond activation, and a lot of groups are working on this kind of chemistry. I'm not going in details, but all those groups' names are here. The Laura, the Jennifer Laura Schoffer, Nielsen, Wang, Westridge, Don Tilley, many people are there. So we wanted to utilize them both in terms of small molecule activation and followed by some different catalytic activities such as hydroboration. You can utilize them with the hydroboration of aldehyde, and you can also utilize them in the hydrosilylation reactions with the typical selectivities with the different silane you can achieve. All right, this is another study that Jaffer made with a borane and silane activation. This is the example of a borane activation of the same Ruthenium cycle, ruthenium nitrogen carbon sulfur bond. And it's very clear, as you could see, that a borane gets inserted to this ruthenium nitrogen bond and it makes a ruthenium sulfur carbon nitrogen 5-member ring. Now, interestingly, when this borane is replaced by a little bigger borane, like B-acetyl borane, the reactivity is a completely different. What happens, it leads to the formation, of course, we have some insertion, but it forms a bis-hydrate borate compound. We have tried this one. This is a typical NMR. I'm not going in details. These are the extra structure. Now, when we have done this one, or we kept this molecule in air or in NMR tube or Schlenk tube, it's converted to a molecule that turned out to be a paramagnetic in nature. As you could see here, its G value is 2.16. We are working currently on this molecule, so I don't want to disclose a lot of the studies here. But this molecule, again, is extremely reactive, and a lot of reactivity is now going on in our laboratory. Now, another interesting molecule with this EPR active molecule is, again, it's a borane activation, and you get all different types of molecule. The molecule number 9, as you could see here, is a bis dihydroborate species, in which you have a cis and a trans isomer, and that both we have isolated. And another molecule that is a very typical, we do not know how to call this, but it's a kind of double, like insertion of the boranes to both sides of the metal center. So these are all unpublished results, so we are working on it. Now, this molecule again is very reactive towards different silanes, and here again it activates the ruthenium nitrogen bond, not the ruthenium sulfur bond. We have very good proof now why the ruthenium nitrogen bond is always active center, not the ruthenium sulfur. And we have shown you earlier that borane activation. Now, one of my students, Subham, is also working on phosphine activation. That goes very well. That study, although I'm not going to discuss today. But silane, some of the examples I had listed here, if you treat them with a different kind of silane, it leads to the formation of a silane activation. And if you heat this molecule, you have a trisilane with the coordination of a ruthenia. This is very unique molecule. A similar kind of molecule was reported some time back by Sylvain Saboitin with a different ligand. Our molecule is exactly same, that is listed here on the left-hand side with extra structure, in which you have a hydrogen, and this hydrogen actually shuttle between among all these 3 silicon atoms. So it was a very nice study. Although the Sylvain Saboitin did a neutron diffraction study to see the connectivity of the hydrogen with the metal as well as the silicon. But as you all know that we don't have that infrastructure to have this neutron diffraction the way you want it. So we had to be restricted to it only extra structure. So this is the extra structure of this molecule, silane activation. This can again be utilized, the same molecule with the alkyne activation, and that leads to the formation of different kind of hydroamination, hydrothylation reactions. So I'm not going in detail. So this is a very good examples. We have made several molecules of the ruthenia cycles, and now a lot of reactivities now is underway in our laboratory. Hopefully, we'll come up with a lot of different. One of the molecules now we are targeting is the synthesis of ruthenium silicon double bonds, and hopefully we'll be able to get the structural characterization of that molecule. Okay, now another molecule that we wanted to extend this study with molybdenum. So this was done by Subham. It's another molybdocycle with a similar kind of chelate linkage, and we see a similar kind of boron activation with this typical molybdocycle molecule. Okay, I think probably I should stop it. Let me just summarize my talk today. What I have talked about different kind of clusters molecule, in which I have shown you the first time 16 vertex metalloboron. Probably now I cannot call it as the first time ever we met, because my friend is also in this list, having 16 vertex. B7 molecule, B8 molecule, and the B6 molecule. Now we have shown you different type of polyhedral clusters that was missing many in the textbook. I'm sure once they are established, many of the textbook will come up with all those. Some of them already there in the textbook now. This is the diboron chemistry I talked about. The left-hand side is an anion, diboron B2H5 anion, and then the another diboron in which you have a metal boron, almost like a flat 180 degree a diboron having one side is connected with the metal. And then a small molecule activation and the catalytic activity using a metal ligand cooperative effect. This is one area now we are strongly working, and hopefully we'll be getting different kind of catalytic activities utilizing this molecule. I have not discussed much of the chemistries on the cluster chemistry now. A lot of people are working on cluster chemistry. They're very, very interesting. In fact, that's one of the areas I would love to practice since till I retired, because this is one area you get a lot of fun, both in terms of electron counting, then you have geometries and many more. So this I would like to thank my group. Many of them are not listed here because now during the COVID time, I am not supposed to take a group picture with my group. Currently, I have 20 to 23 students. All of them, a couple of them are postdoc and all 20 are PhD students. Some of the pictures, probably Sahu, you can recognize, Suvankar, Gita, Dhayal, that they came during my 50th birthday. And all others, actually, the co-workers. I have already acknowledged the co-workers while presenting my talk, so I'm not going to mention their names here now. Two of my big pillars to do this chemistry is Jemis and Babu Varghese. Without their help, probably, this kind of chemistry would not have possible here in IIT Madras. So I really thank them a lot for their enormous support since we know them almost 30 years. So it was so nice, so sweet of them. Then Licensing 1, Jeff Halley from Rains and Brown University. Funding agencies, in particular IIT Madras, DST, ACRB, and CSR for supporting a lot of fundamental chemistry, although we are currently working on many applications. But initial stage, they have supported a lot to do a fundamental chemistry. Then Indo-French CPIPRA for supporting this, again, fundamental chemistry on the silane and boron activation with different the chelate complexes. And finally, thank you very much for being in this lecture, and I'll be happy to take questions if you have any. Thank you very much.
Thank you very much, sir, for your nice presentation. Now the session is open for discussion. So there is one question in the chat box. So what is the stabilities of the cyclopentadiene and the benzene ring?
That is your benzene or the B6, which one?
I mean the CP. I mean probably this is the. I mean CP which is attached to metal and the benzene ring. If you substitute like CP with benzene, I mean how does the stability vary?
Okay. Oh yeah. See, if you, I think probably Sahu, you should answer this question. You should know it.
So today,
Okay. I will not put you in false position. Okay, I'll answer this question. So the thing is, CP is anionic, CP minus. So that means metal will be connected with the CP, like with the plus charge, and benzene is a neutral. It's a eta 6. The stability of the benzene will be always weaker than a CP ring. And that's why whenever we have studied any kind of like a parathymine, it's very difficult to retain this benzene ring in many molecules. So that's why if you start any chemistry with the benzene, we don't have much success. Some exceptions are there, like arene chromium complexes with the chromium CO3 benzene. That stability comes in a different fashion, not with this kind of thing. I hope that I have clarified the questions what the student asked.
So the students are encouraged to ask questions. I mean, I request the students if they have any questions, they can just go ahead. Many of our MSc students are here.
Excuse me, sir.
Yes, sir.
Sir, you said the B12 H12 2 minus is the most stable boron. So why? What is the reason?
Well, I mean, B12, H12, see, this is a theoretical calculation, and that's what they propose. And all the studies, it shows that it's the most stable one. I do not know exactly the reason, but I believe it could be due to the highest symmetry. It has the maximum symmetry you could think of it. Very, very symmetric molecule. And you take any of the icosahedral B12 geometry and you see everywhere, you rotate it like octahedral geometry, you always end up getting a same view. So it has a very, very high symmetry. And because of this symmetry, I believe that this is extremely stable conformation, stable among all the others.
Thank you, sir. Chandan Panigrai, sir.
So is there any more question from the students and from any participants?
Should I stop sharing this screen?
Yeah, yes, sir. You can just stop sharing. Okay, sir. There is one question from one of our students. What make boron to form? I mean, 3-center 2-electron bond.
Say it again.
What make a boron to form 3-center 2-electron bond?
What makes boron? Okay, so this is very simple, no? I mean, like if you take a carbon, now it has a 4 electrons. So that means if you have your 4 ligands, they come with 1 electron each, and it's an octet. So it follows the octet rule. But when it comes to the, say, BH3, now BH3, hydrogen gives 1 electron, boron has 3 electrons. So it is now 6 electrons. So this boron is the only element in the periodic table that do not follow the octet rule. All others you see. So this is very, very exceptional. That's why we have a sextet rule for the boron. And because of that, so it has to fulfill the 8 electron rule in terms of the 3 center 2 electron bonding. Now, if you take a diboron, it has no other choice. But now, not only 3 center 2 electron bond, now 4 center 2 electron bond is very well established now by theoretician, and this is well known. Only with boron, but now this has been also extended with the other metal, particularly with the zinc ions.
Other questions on the student sides?
So how many MSc students you have now in your?
Sir, we have basically like 50 plus 50. So total 100 students.
Okay.
But these second year students, they are appearing their examination, third semester examination. So many of them are not like present.
Okay.
And only first year students are there.
Exams are now online or
No, no, in Odisha, it's going like in physical mode. Our classroom teaching as well as this, examination, they are in physical mode.
So if something goes wrong, Modi will catch you then.
So maybe government is going to impose very soon and some restrictions. Okay,
So
probably.
finish the exam as soon as possible.
So I think there are no more questions. So if there is no more questions, let me thank my supervisor, Professor Bose, for giving a nice, wonderful talk. Actually, I have also listened to you, sir, after quite long time. Many of, new things I'm also listening. Okay. So thank you very much for being with us.
Okay. Thank you.
Thank you very much, sir.
Thank you, sir. See you again and again, sir.
Okay. Thank you. Looking forward to visit your school.
Sure. Yes, sir. You are invited to our university, sir.
Okay. Good. Okay.
Thank you,
So I'll take your leave now, Sahu.
Okay, sir. Okay, sir. See you then. Okay, so thank you, dear participants. So we'll close the session. Now. So tomorrow again at 9:45 a.m. in the morning we'll join for our second day. So in the morning session we have 2 lectures, like 10 to 11:30 and 11:30 to 1. And in the afternoon session we have one more lecture, that is 2 to 3:30. So please join tomorrow sharp at 9:45 a.m. So till then, take care. Goodbye. Bye-bye.